Welcome back. Our next example is talking about how we use the equilibrium constant in order to calculate concentrations of things at equilibrium. Is one where we're now starting with NaCl and producing NO and Cl2. And we're going to start again with all reactants. We're working on that for now, and we'll get to times when we don't start with all reactants later on. And no products at all. Our K here is very small, so it's about 1.6 times 10 to the minus fifth. And if you remember, what does that mean about our reaction? If we remember a small k, right, in order to get k products over reactants, in order to get to be small, you either have to have a very large denominator, which you can't really have with concentrations, or very small numerator, which you can have with concentrations. So we're expecting to have very small concentrations of our reactants. And that's going to be really important for how we solve this reaction. But we do everything exactly the same way. We write out our ICE table, we write down the K expression, we substitute it in, and then we try to solve. So let's see what this problem brings to us. So we're going to start out by writing our reaction over again. 2NoCl goes to 2NO plus Cl2. I don't know why I put a square there, Cl2. And then we'll do our ICE table, ICE. And we're starting with 0.50 molar NoCl. None of this and none of this. As it reacts, we make some. We don't know what it is. We call it x. And then we do the stoichiometric coefficients 2x. We're using this one up, and so we say that one is minus 2x. We add them up to get the equilibrium line. We get 0.50 minus 2x, 2x, and x. We write our K expression. K is equal to the concentration of NO squared, the concentration of Cl2, over the concentration of NoCl squared. Checking, always check, always double check that you've done your superscripts properly, you've done those squarings and things like that. One of the most common mistakes in these type of problems is to forget to put a square, just one of them. It's actually not common to forget to put all of them. It's common just to forget one because you're not paying attention. You forgot the square on the NO, or you forgot the square on the NoCl. So it's something really important to pay attention to. And that is equal to 1.6 times 10 to the minus fifth. We're going to substitute in our equilibrium line here for all the different concentrations in that expression. And so what do we get? We get that K is equal to 2x squared. And again, I'm going to remind you, always put that 2x in the parentheses, because that's your concentration. Your equilibrium line says your concentration is 2x. The equilibrium expression says you square that concentration. People always want to put it outside, but you got to put it inside. And then we write x. And then we write 0.50 minus 2x squared is equal to 1.6 times 10 to the minus fifth. If we kind of write that out a little bit, we're going to get 4x cubed over 0.50 minus 2x squared is equal to 1.6 times 10 to the minus fifth. And at this point, you should be pausing and thinking, the cubic equation, I don't remember the cubic equation. You probably never learned the cubic equation. There are ways of solving cubic things by using an equation, but they're tedious, they're hard, they're not something you're going to remember off the top of your head like you possibly might remember the quadratic formula. So how are we going to solve a cubic? And it comes down to, again, right, Professor Clements, I can just type this into to Google or to Wolfram Alpha, it'll just solve it fine. Can I just do that? And the answer is no. You can't. I don't want you to do it that way, unless I ask you to. There's a couple times in the class where I say, just go ahead and do it that way. But what I really want you to focus on is how can we solve complicated problems by making assumptions. And that's what we're going to do here. And why are we focusing on that? Why are we focusing about making assumptions rather than solving a problem that clearly a computer can solve for us? Because there are problems that computers can't solve for you. They can do all sorts of computations and things like that. But sometimes the problem's just too complicated. So making assumptions and learning how to make assumptions, what assumptions are reasonable, how do we check our assumptions, how do we know whether our answer is reasonable given the assumptions that we have, those are really important skills to learn early on when we can really check our work, right? Because there's going to be problems so big that you can't plug it into a computer unless you make a few assumptions. And then when you make those assumptions, then you can plug the stuff that the computer's good at into the computer, and it'll help you solve things. Absolutely, great, use it. But you have to know how to do that, and you have to know how to check to see whether it's reasonable. And so that's one of the skills we're learning in this part of the class, is not how to solve a cubic equation, but how do we solve complicated problems by making assumptions, checking those assumptions, and seeing whether they were reasonable. So what are we going to do? Well, if you remember, I said because k was really small, we expect very little product. Right? We don't know exactly how much, right? Because that's what we're solving for. But we expect very, very little product. So if we look at this part of our formula, the 0.50 minus 2x. Okay? And we say, let's just say we expect very little. We've got a 10 to the minus fifth here. Let's just say that x ends up being 0.001 molar. Okay? It ends up being a very, very small number. Now, if we look at that, minus 2 times 0.001, what does that equal to? 0.5 minus 2 times 0.001. Well, if you look at it from a mathematical point of view, you're going to get 0.499, actually 0.498, sorry. But if you look at it from a significant figures point of view, we only have 2 digits after the decimal in that first number. We've got 3 digits after the decimal in that second number, so we're really only going to have 2 digits after the decimal, and so you get 0.50 back. And so if x is sufficiently small, then 0.50 minus 2x is approximately 0.50 if x is sufficiently small. Now, we've got a chicken and egg problem right here, but we don't know if x is small until we solve the problem. And we're going to use the fact that x is small to solve the problem, and the answer is yes. We're going to make that assumption right now. We're going to say, hey, because my k is pretty darn small, I'm going to make the assumption that my x is also going to be pretty darn small. And it's going to be negligible compared to 0.5. And I can make this assumption right here, that 0.5 minus 2x is about 0.5. Because what does that do? If I come back up here, I've got to copy this one down some more. So I'm just going to copy it down 4x cubed over 0.50 minus 2x squared is equal to 1.6 times 10 to the minus fifth. If I make the assumption that this is approximately 0.50, my expression reduces to 4x cubed over 0.50 cubed equals 1.6 times 10 to the minus fifth. And boy, if that isn't a whole lot easier to solve, right? I cube that 0.5, whoop, I square, okay? Sorry about that. See, it's really easy to make little mistakes, and these powers, most common mistake in these kind of problems is just powers disappearing, powers changing as you go along, because it's really easy, right? You're cubing things, you're squaring things, and you accidentally cube or square the wrong thing. So pay attention to that as you go. So I just square 0.5, I get 0.25, and so I get 4x cubed is equal to 0.25 times 1.6 times 10 to the minus fifth. I divide both sides by 4, and then I get that x cubed is equal to 1.0 times 10 to the minus 6. And if x is 1.0 times 10 to the minus 6, x cubed, I'm going to take the cube root of both sides. And your calculator knows how to do the cube root. If you don't know how to do that on your calculator, you can probably look it up. If you're still having difficulty with it, absolutely come and talk to me, and we can figure out how to do that on your calculator together. So the cube root of that is going to be 1.0 times 10 to the minus 2, or 0.01. Now, if you look back up, we had 2 sig figs in most of our numbers, and so I'm going to put that as a 0.10. And it's going to have a unit on it, since now we're starting to talk about our concentrations individually. All right, so if we look back up at our ICE table, we figured out that the concentration of NO was 2x, and so that's going to be 0.020 molar. The concentration of Cl2 was x, and that's going to be 0.010 molar. And the concentration of NaCl was 0.50 minus 2x, which in this case is actually going to be 0.48 molar. Now, in my example I used above, I said, hey, if it's really, really small, 0.001, then it doesn't even affect the value of my thing, and I still get 0.5, right? So now it is, right? It's actually a little bit big enough that it's affecting my number, and I get 0.48 molar, not 0.5 molar like you said I would, Professor Clements. Is that okay? And that's where checking our assumptions comes into play. We've made this assumption, and now we have to say, did the assumption, what we call, hold water? Is it a reasonable assumption? And the criteria that people generally use for testing the assumption, and I require you to do this when you're writing out these kind of problems, it's part of your grade, I need to see that you actually did this test, is you're going to take and just divide x, whatever you calculated x to be, and you're going to divide it by what you assumed it to be small compared to. So, right, we were saying that 0.50 minus 2x was approximately 0.50, right? That was our assumption. And so now we want to test that assumption. Now, you really should test for 2x over 0.50, but every single textbook I've ever seen, and I looked through, I don't know, 30 of them one day because I was very curious, has you testing x over 0.5 for this type of problem. So I'm going to do that. I really think I should be testing 2x over 0.5, but the other people who maybe know a little bit more than I do always test over x over 0.5, so I'm just going to go ahead with it. Again, if there's any smart people in the audience there who understand why it's always that way in every textbook I've ever found, let me know, and I'm happy to learn something new. So what are we going to do? We're going to take x and divide by 0.50, so we've got 0.010 divided by 0.50, and so you get 0.02. And that we're going to turn into a percentage is about 2%. And what we said is our assumption is good to about 2%. That's what that means, is we compare x to the thing we said x was small next to, and we get about 2%. Is that good? And it depends on the problem. I mean, if you're trying to do something extraordinarily precise, then 2%, that's probably not good. But it turns out in these kind of problems, a 2% difference in that makes very little difference in the final answer. You could go ahead if you want to. Go ahead and plug this equation back into like Wolfram Alpha or something like that and see what answer it gives you. It's not going to give you exactly 0.010, but it's going to give you something awfully darn close to that. And to a couple significant figures, we're probably not even going to notice the difference between the exact solution and our assumption solution. So 2%, what we're going to say is the criteria for a good assumption is that this check will be less than 5%. Okay. Now, Professor, what is exactly 5%? Is that okay? It's on the edge. It's on the edge, right? It's a made-up number. I mean, 5% is just a made-up number. Somebody could have said 6%, 4%, but you know, people who have done this for a long time said, hey, look, if it's less than 5%, it's probably going to affect your answer so little that it's not going to make a big difference to it. And that's what we're going for. We're trying to get a good enough answer. No, let's get the exact answer. Sometimes good enough is all you get. Like I said, we're not really doing it to show how to solve this kind of problem as much as learn how to solve more complicated problems. So because R is less than 5%, our assumption is good. And it never hurts to actually write that down, right? After you do that little check, write down the assumption is good, and that way I really know that you understand what you were doing in checking that assumption. Okay, or the assumption is no good, and we'll figure out what to do in that case in just a moment. So now that we know our assumption is good, we can actually go back and say, hey, these are our equilibrium concentrations after we allow this thing to come to equilibrium, and it's good enough. And like I said, go ahead. I highly encourage you to plug in exact numbers into Wolfram Alpha and see what you get, and you'll find it's very, very, very close to this. So that's how we solve problems where we have a very small x, where we know we're not going to produce much, and we can ignore that x in one of our terms, or sometimes even more than one of our terms, in our equilibrium constant. So we just ignored the x there, and then we verified that that was a valid thing to do as long as it's less than 5% is our criteria. So turns out this is by far the most common method we're going to see for solving these type of equations in this class. We're going to use this method over and over and over and over again. So become familiar with it, and how you become familiar with it is by practice, so don't worry, you'll get lots of chances to practice that in this class. So our next problem looks fairly similar. We've got 2H2S goes to 2H2 plus S2. Our initial concentration is 2.5 times 10 to the minus 4th molar H2S. And our K, again, is very, very small. We don't expect much product. 1.67 times 10 to the minus 7th. And we're going to find our equilibrium concentrations. I'm going to go through this pretty fast since this is our 4th time making our ice table. So we got 2H2 plus S2. We got ICE here. Initial concentration 2.50 times 10 to the minus 4th. No hydrogen, no sulfur. We're going to react 2x, make 2x, make x, right? All those stoichiometric coefficients. We're going to add that up and get 2.50 times 10 to the minus 4th minus 2x, and x. We write our K expression, which is going to be the concentration of H2 squared, the concentration of S2, over the concentration of H2S squared, and plug in our equilibriums. Right? Let me make that equal to our value, which was 1.67 times 10 to the minus 7th. And we're going to plug in our values down here, and we get 2x squared x, let me make a bit of parentheses there, over 2.50 times 10 to the minus 4th minus 2x squared equals 1.67 times 10 to the minus 7th. And we look at that and we're like, well, we expect very small x's on top, right? How small? We don't know. But let's go ahead and try to make the small x assumption, is what it's called. And then again, it's a good idea to write that on your papers when you're doing it. Hey, I'm actually making the small x assumption. I know that's what I'm doing, so I write that down. And what is that? It's that 2.50 times 10 to the minus 4th minus 2x. Because x is small, we expect x to be small, is 2.50 times 10 to the minus 4th. They'll be approximately equal whether or not we include the x value or not, which simplifies our K expression. We now have 4x squared times x over 2.50 times 10 to the minus 4th squared equals 1.67 times 10 to the minus 7th. I'm not going to do all the math for you here, right? I got to square that number, multiply it by 1.67 times 10 to the minus 7th, divide both sides by 4, and I get that x cubed is equal to 2.61 times 10 to the minus 15th. So I'm going to cube root both of those sides. And I get that x is equal to, 1.38 times 10 to the minus 5th molar. Okay, that's a pretty darn small value. We definitely got a small x, but what do we always have to do? We always have to check our assumption. So we're going to check the assumption. And we're going to compare the x that we got over the thing we thought it was small compared to. And so we get 1.38 times 10 to the minus 5th divided by 2.50 times 10 to the minus 4th. We plug that in our calculator, and we get 11%. So you'd get 0.11, you'd multiply it by 100 to get 11%. Wow, 11% is greater than 5%, so it means we have a bad assumption. We made a bad assumption. It actually turns out it's not true that our x is small compared to our value. And so we're saying, hey, we can't make that assumption here and think that we did a good job. So there's two things to do. One is you go back and maybe you try to make a different assumption. Or you go back, more than two things. You go back and you try to solve it by an entirely different method. Again, this one we could solve exactly by telling a computer to solve it for us. The other is what I call the method, or what people call the method of successive approximations, is what we're going to use next. And you're going to have to use this method as well. If you find you get a bad assumption, we're going to do the next step, which is to try to make our assumption better. How do we make our assumption better? Well, our first assumption was that x was so small compared to our value of 2.50 times 10 to the minus 4th that we can ignore it. We said, hey, we're gonna get a value out of here, we're going to ignore it. And in the last problem, that worked really well. In this problem, it didn't work really well. So what are we going to do? We're going to say, well, we're not going to say x is negligible. This was saying that x was so small, it was negligible, and we could just ignore it. Now we're going to say, well, maybe x isn't so small to be negligible. 11% isn't horrible, right? If you were just trying to do what's called a back of the envelope calculation, it might even be good enough. It gets you close enough to the answer. So we weren't awful in our assumption. I mean, if we got 75% there, we'd probably go back and we'd have to use a different method because we were way, way off. But 11%, we're not that far off. And so we got a value for x here of 1.38 times 10 to the minus fifth. And although it's not perfect, it's probably not bad. And so what we're going to do next is we're going to assume that x is 1.3. What did I get? I already forgot the number. 38 times 10 to the minus fifth. For the purposes of comparing it to our 2.5 times 10 to the minus fourth. You're like, what? That just went over my head. Hold on, just a moment. What did we have? We had 4x cubed over 2.50 times 10 to the minus fourth minus 2x squared. And that was equal to our k value, which was 1.67 times 10 to the minus seventh. And at first we said, hey, x is so small, let's ignore it. And we figured out that that's not a great assumption. But now what we're going to do is we're going to assume that x is this value. Now, if you just plug x in for that value here, and you plug it in down here, you're just going to get a number on one side and then comparing that to a number on the other. And you're going to find that it's not entirely true that x is that size that you think it is, and so it doesn't work. So it turns out the only place we make that assumption is not in this 4x cubed. We're not going to assume the 4x cubed. We're going to make the assumption in the exact same place we made it last time. The exact same place we made it last time was in this part, the subtraction part. Sometimes it's an addition part. It doesn't have to be subtraction. That's where we're going to make this new assumption that x is about 1.38 times 10 to the minus fifth. And so with our new assumption, it's going to turn our equation to look like this. 4x cubed over 2.50 times 10 to the minus fourth minus 2 times 1.38 times 10 to the minus fifth squared is equal to 1.67 times 10 to the minus 7. So you see what I did there? All I did is I took this x that I calculated in my first iteration that I thought wasn't good enough. It wasn't horrible, but it wasn't good enough. And I substituted that into a next round and said, hey, if it wasn't good enough to assume that it was 0, right, which is essentially the assumption we were making, let's see if it's good enough to assume that it's 1.38 times 10 to the minus fifth. And so we're going to go ahead and plug that in. Now that's just a bunch more math, right? You have to do 2 times 1.38 times 10 to the minus fifth, subtract that from 2 times 10 to the minus fourth, square that, multiply it, divide by 4, take the cube root. I'm not going to do all that math for you. And what I get is that x, if I solve this, is 1.27 times 10 to the minus fifth. And so I went from 1.38 times 10 to the minus fifth to 1.27 times 10 to the minus fifth. Now, this next part is usually a little bit confusing for people. Question is, how do I know, is this good? You know it's good if it didn't change much from your previous x. So we're going to compare our first x, number 1, 1.38 times 10 to the minus fifth, and to our second x, 1.27 times 10 to the minus fifth. And unlike our previous one where we had a fixed criteria of 5%, this one's a little more judgy, kind of hand-wavy. And there's a good reason for that, is because we're not going to go into this any further. Look, 1.38 to 1.27 times 10 to the minus fifth, that's not a big change. If your second x was, 5 times 10 to the minus third, that would be a huge change. You'd be talking 100 times, 500 times the value of x. Here, we're talking very small fractional changes, percentages, a few percent change in x. That says that we're good. Small change equals good. And here's a hint. In this class, you're never going to have to go past one of these steps. What happens in real life, and this is actually a way computers solve it as well, it's a little more complicated, but they do that assumption. They make an assumption, they check it, and they change the value of x to be more in line with a new assumption. And they check it, and they put a new value of x and check it. And you can do that hundreds of times in a row. Computers can do it millions of times in a second, or billions nowadays, or trillions even almost. And so that's actually how you can solve these kind of very complicated problems in real life, the method of successive approximations. In this class, we're never going to go past that second one. So we assume x is 0. We find out that that's not good. We assume x was our new x. And then that's always going to be good in this class. So that's a hint for you. Okay? But that's how we check. If you got a huge change, you'd be like, that's no good. But since we got a small change, that's good. And we're going to say x2 is our x value. And we're not done yet because our goal was to find equilibrium concentration. So we've got to go back to our ice table and find out that the concentration of H2 was 2x, the concentration of S2 was x, and the concentration of H2S was 2.50 times 10 to the minus fourth minus 2x. This one's easy, 1.27 times 10 to the minus fifth. This is going to be 2.54 times 10 to the minus fifth molar, don't forget those units. And then this one is a little more complicated, and I'm just going to look it up instead of trying to do it in my head. We get 2.2 times 10 to the minus fourth molar. So there we go. We've got equilibrium concentrations for all three of our species by using the small x assumption, and then when it wasn't good, using the method of successive approximations. Take a breath. All right. Here's just a quick one for you to try, just checking in on the stoichiometry of these ice tables with you. I've got this reaction here with a K. I start off with these following concentrations. Those are my initial values. And I want to know what are my equilibrium concentrations in terms of X. So you're going to pick line A, B, C, or D as what you get on that E line in your ice table. That's what you're going for. You ready? Okay. Let's see what you got. Well, what do we have? We have our ice table. N2, 3H2 goes to 2NH3, ICE. What do we have? Well, we have 0.15 molar for our H's. We've got, for our N2, we've got 0.05 molar for our H2. Then we've got a 0.2 molar for our H3. And some people do want to do things here where they're like, well, shouldn't I multiply that H2 by 3 since I got a 3 there? No, no, no. That 3 tells you stoichiometry. When things change, when I'm making H2 or when I'm using up H2, I have that stoichiometry of 3. But if someone just tells me I've got 0.5 molar H2, I've just got 0.5 molar H2. So the question then is, well, which direction is this reaction going to go? We have both reactants and products. So am I going to get positive X on the right? And that's what most people do. By default, they'll just say, oh, if this is going to be a 2x, this is going to be a minus 3x, and this is going to be a minus x there. But how would we know? How would we know for sure which way this reaction is going to proceed? If only there was a way to calculate which direction a reaction would proceed. Wait, there is! Do you remember our good friend Q? Right? Q just says, hey, let's plug in our current concentrations into our equilibrium expression and compare that to the value of K. And so we get 1.5 molar and 0.05 cubed. It's got to be a cubed. And what do you get when you do that? You get that Q is 213.3. So Q is greater than K. And if Q is greater than K, the reaction shifts, you remember? Left. The reaction shifts left. So we actually don't get more products made, which was kind of our default thing to think. And that's totally understandable. That would be your default thing to think, because every chemistry you've ever done have always said, well, let's make more products. But that's not always the case. In this situation, we're actually going to make more reactants. So I'm going to go ahead and switch these guys. I'm going to lose my products, because that's what shifting left means, and I'm going to gain reactants. Okay. So what do I get? I get 0.15 molar plus x, 0.05 molar minus 3x, and 0.2 molar minus 2x. So which one does that correspond to? 0.15 plus x is only in C there. So plus down there. Sorry about that. A plus 3x there in my equilibrium line. And a 0.2 minus 2x. So if you did go ahead and get the opposite one, where you had the minus 3x and you had the minus x, but then you had a plus 2x, and so it looks like answer D, you're doing okay. But you have to remember that reactions don't always go to the right. Sometimes they go to the left. What would actually happen is if you solved that, is you'd get a negative value for x. And that negative value, initially you'd be like, well, can't have negative concentrations. But remember, your x is a change in concentration in this case. And so if you plugged it in, you'd actually get some reasonable numbers, and you'd be OK. But it's best to know which direction the reaction goes by calculating Q first. OK, so that was a little tricky on purpose. Hope you got that one OK. Thanks for listening, and we'll talk some more in a little while. Bye.